Yes, so thank you very much for the introduction, and thank you very much for inviting me here. It's always a great pleasure to visit Vilnius. So my name is Karol. I'm from University of Innsbruck. I work together with Helmut Rich, and most of the stuff I do is actually cavity QED in the context of quantum sensing, quantum metrology, quantum phase transitions, a little bit of quantum simulation, but most of it is, as I say, in the context of cavity QED. And coming here, I had to come up with some idea, how to combine my research with multi-component simulation. And I remember talking with Thomas Busch when I was still in Okinawa, and he told me about this fact, or what he believed, that actually, if you have this cavity QED setups, you can actually simulate them in spin orbit coupled Bose-Einstein condensate. And I was then at that point like, wow, that's great, because if you go to this BECs, you have so much control suddenly. You can change the interaction. You have an isolated system. So suddenly you open new possibilities. So you can explore all this phase transition, generation of some non-classical states. You can essentially transfer all these technologies developed in cavity QED setups to a different platform with different possibilities. So unfortunately, there is some disagreement in the field. So I was reading papers, and some people claim that, indeed, this is possible. And there is also some experimental works that show this decay phase transition in a BEC with spin orbit coupling. And there are also some other works which say, this is not possible. And during this talk, I will essentially explain what I figured out. And in this sense, this will be extremely elementary and almost pedagogical presentation. So I will start with some motivation. Then I will introduce cavity quantum electrodynamics with some paradigmatic models, like this quantum Rabi model and decay model. Then I will talk a little bit about spin squeezing and many-body entanglement in cavity QED, how you can generate it. And then I will go to this spin orbit coupled BECs and show what is the connection actually between cavity QED and spin orbit coupled BECs. So the motivation, one of the main motivation is this paper from 2010 from the group of Thielmann Esslinger, where they realized this decay quantum phase transition in a superfluid gas in an optical cavity. So this is this celebrated super-radiant phase transition, which is mapped to the self-organizing transition, where atoms organize in a cavity in a spatial pattern. And then, so this is essentially exciting because a single optical mode acts as a quantum bus, a harmonic oscillator coherently coupled to a collective big spin that mediates tunable long-range interactions, generate entanglement, and enables fast, high-fidelity measurement and control on the same platform through the photons going out from the cavity, for example. So this is this experiment that they performed. So there is an ensemble of atoms in a cavity driven by a laser from the side. And if the power of the laser is strong enough, the atoms start to organize in either even or odd sides. And this is this phase transition, the super-radiant phase transition with Z2 symmetry breaking. So there is lots of possibilities, and I think this experiment was run almost forever, maybe even until today, with various changes to it. However, my favorite application of cavity QED is actually this generation of spin squeeze states with non-demolition measurement of the atoms in the cavity. So this experiment essentially relies on putting atoms in the cavity, and once you put atoms in the cavity, this essentially changes the resonance frequency of the cavity. And this resonance frequency now depends on the number of atoms in the cavity. So if you measure it, you kind of non-destructively measure the amount of atoms in the cavity. And if you think about the collective state, spin state of atoms in the cavity, before measurement, you would have some uncertainty in the number of atoms. And of course, if you measure it non-destructively, you gain some information about the number of atoms, which reduces the uncertainty in this population imbalance. And of course, since the volume in the phase space is it cannot be arbitrarily small. This is limited by Heisenberg uncertainty principle. The fluctuations in an orthogonal direction have to increase. Okay, so yeah, of course, there's many other schemes to generate entanglement, non-classical correlations, various setups. And so this is this paper I briefly mentioned at the beginning about this decay type phase transition in a spin orbit coupled boson-Einstein condensate, which was experimentally realized in 2014. And yeah, so simulating cavity QED in spin orbit coupled BECs offers a clean, low dissipation analog where the condensate center of mass harmonic mode plays the role of the cavity, mediating tunable long-range interactions and entanglement without optical loss or spontaneous emission limits, as I told you before. Yeah, so the question is it really the case, or maybe there is some issue with it? So actually, this was already presented by Sarah, this two-Raman photon process and how you can simulate the synthetic spin orbit coupling in the BEC, so I will skip this. So again, this is the question. Can you actually have physics of atoms coupled to a single mode optical resonator simulated with spin orbit coupled BEC? And actually, couple of groups picked up this idea, and they show, yeah, indeed, if you have this mapping, then you could generate this spin squeezing, this field squeezing in BEC just by using the center of mass mode to mediate interactions between atoms. However, there is also this paper from 2020 from the group of Han Pu, which in this paper they are saying that, yeah, it was shown that the map decay model leads to spin squeezing. So these two previous papers, which implies that spin squeezing can be generated from SOC alone without the need of interaction. This, however, contradicts our intuition that spin squeezing is a consequence of interaction-induced quantum correlation between the atoms. So this is clearly not true in the context of cavity QED, because clearly you can use photons to mediate interactions between atoms without direct atom-atom interactions. And here they write, this result can be traced to the mapping, which in our opinion results from some unjustified approximations. But they never really tell what are these unjustified approximations. So I will tell you essentially what is happening here, whether the intuition they have is right or maybe it's wrong. Okay, so we start with something extremely simple. Two-level atom in a cavity. So this is the field operator, so frequency omega of the cavity, coupling between the cavity and the atom. And this is one of the simplest models in cavity QED, quantum Rabi model. Of course, it exhibits this quantum phase transition, the super-radiant phase transition. So in this sense, super-radiant phase transition is not a many-body effect. It can be also realized with a single component system. Just one atom coupled to a harmonic oscillator is enough for showing this phase transition, which was simulated. So this is a theoretical paper, but of course it was also simulated in other platforms. And what I am interested in is, of course, not single particle physics. I am interested in many-body physics, where you put lots of atoms in the cavity, and now this becomes a decay model where cavity, so this field A dagger interacts with entire ensemble of atoms. So now we have a really many-body problem. And in order to simplify it, and look at some particular feature that is really many-body, I will look at this spin squeezing, which derives from mediated atom-atom interaction, and how can you see that this Hamiltonian actually leads to squeezing. And this effective spin model, you essentially go to a limit where the frequency of the field of the field is much larger than the frequency of the two-level systems, and this is typical limit in physics. You just eliminate the component with much larger energy. So in this case, you eliminate the field degree of freedom, as we saw in the talk of Kuba. We end up with this effective spin Hamiltonian, which is this all-to-all interacting Ising model or Lipkin-Meshkov-Glick Hamiltonian. And in principle, the interactions between atoms can be mediated by vacuum or virtual excitation. So you don't really need a laser that lights, that somehow shines on the cavity. This just arises because atoms interact with vacuum of the electromagnetic field. Okay, so this is actually how this, this presents the ground state of this Hamiltonian as a function of this interaction parameter normalized to omega. And and here I show this squeezing parameter, which essentially looks at quantum fluctuations of the spin in directions perpendicular to the mean direction of the spin. And actually, there is a very nice criterion for squeezing parameter. If squeezing parameter is smaller than 1, this shows entanglement in your many-body quantum system. So here we precisely see what happens once you change the light-matter interaction. You create entanglement and spin squeezing until some point. And because this is g to the power of 2, so it doesn't really care about the sign of g. And this shows that, yeah, indeed, you don't really need direct atom interaction to generate effective entanglement in many-body systems. Oh yeah, so this is another depiction of squeezing on this phase space, right? So this is a generalized Bloch sphere. So these dashed lines would be coherent state, coherent spin state, whereas this color scheme here inside is the squeeze state, where we see decreased fluctuations in x direction and increased interaction in fluctuations in y direction. And yeah, so if really these two pictures are equivalent, it should be possible to use the center of mass excitations to mediate interactions between the spins. So let's see how to do it. Let's start with a single particle picture. So yeah, so here we have effective spin-orbit coupling Hamiltonian for a single particle. So we have the momentum part, the spin-orbit coupling, some extra interaction, so coupling between the two levels, the energy mismatch between these two coupled spin. And now if we play a little bit with this Hamiltonian by introducing this field operators for the center of mass excitations, we get to this form. And this is almost identical to quantum Rabi model. Of course, there are differences. So first of all, we have here coupled to momentum, not position, but this is simply rotation by 90 degrees in the phase space. And also, we have this term, which is kind of the tuning, which can be easily set to 0, so we can eliminate this. And one more difference is this x and z here, and this x and z here. But again, this is just a simple rotation on the Bloch sphere, so it doesn't really matter. It would be a perfect simulator of a quantum Rabi model. So definitely, at least at the level of single particle physics, spin-orbit coupled BECs can be used to simulate cavity QED. But of course, what I'm interested in and what is much more exciting is this many-body aspect of it. So whether spin-orbit coupled BEC can simulate the decay model, where instead of having a single atom coupled to a cavity, we have now an ensemble of atoms coupled to the cavity. And now you already see on this level that there is some difference in the Hamiltonian. So first of all, here we have this extra sum over the harmonic oscillators. And in this sense, this SOC BEC, it's as if you had like many harmonic oscillators coupled to many atoms. So definitely there will be some differences between these two Hamiltonians. The question is, what is the difference, and whether it gives you something new or maybe it limits you from doing something interesting actually. So of course this is hard really to do it because this is a many-body problem. So if you wanted to do it numerically, I mean, you are limited quite a lot. So what we do is something extremely simple. We just take two atoms and see what really happens. So if you just take two atoms, you can introduce this coordinate change to the center of mass mode and the relative mode. And if you rewrite this SOC BEC, which is just two atoms in this case, you clearly see that you have a term that is a decay model term, and also you have some extra coupling. So now let's see how these two guys act separately. So now, if I have this Hamiltonian, I can easily play with it numerically. So I can essentially turn this to 0, or just turn this to 0, or just see what really happens. So first of all, let's look at the case where I set this to 0, and I only have decay model term. And then you clearly see that if I look at the fluctuations of the spin in two directions, so x and y, one goes up, so this is this anti-squeezing we saw on the Bloch sphere, whereas here we see that this is squeezing, so going down, which we also so on the generalized Bloch sphere. And now I can do the other way around. I can turn off this and turn on this only. And in this case, I see that actually I reverse the squeezing, right? So I increase the fluctuations in X and decrease the fluctuations in Y. And if I add these two terms now, so I set this equal to this, I see these two effects actually interfere destructively, and I have no net interactions, so no net squeezing. But maybe this is just a few body effect. Maybe something more interesting happens if you add more atoms. So of course I can go to 3, but so again, this is this squeezing, which you would see with having just the decay model term. It would look like this. So the fluctuations S, X. This is for this extra coupling term, which is reversed by 90 degrees essentially, and this is what you will see if these two terms compete at the same time. So yeah, as I was saying, in principle, I could go just to 3 atoms, but let's just jump to 4 and see what happens. And now to somehow tackle this problem, I introduced this relative Jacobi modes and center of mass mode. So I use this P and QK to rewrite the Hamiltonian in a way in which I can analyze suddenly easily what is happening and see with my eyes directly what can I do with it and what I cannot do with it. Okay, so it looks like this. So what we see here first is this decay model interaction. We have this extra 2-body coupling, which we saw before. We have also this 3-body coupling, an extra 4-body coupling. And I call this 2, 3, 4-body coupling because I have here 3 operators from the spin. Here I have 2 operators for the spins, and I have 4 operators for the spins coupled to some relative mode. And okay, once I have this, I can again play with different terms and see what is really happening to kind of get an intuition of what I can achieve with this simulator. So again, if I add all the terms simultaneously together with the same interaction strength, I get absolutely no redistribution of quantum fluctuations. So I get absolutely no squeezing. Whereas if I look on the decay term, then of course I get squeezing, as theory predicts. And if I look only at this extra couplings, I see that I also get squeezing in other direction, but it is not as strong as just for the decay term. And yeah, so if these two guys compete at the same time, I of course get no effective net squeezing. And yeah, so this goes back to this initial questions. Can I really simulate this physics with spin orbit coupled BEC? And of course, as we see, it's not that easy because here you have much more terms which you would have to control in an experiment to really simulate the decay model. And in this sense, we see now what is this unjustified approximations that this experimental paper I showed before, and these 2 papers about generation of spin squeezing made. You cannot just take a Hamiltonian and remove the parts that you don't like. You really need to keep everything together to see the effective physics. So essentially what they did in these papers, they did this and just saw this in the Hamiltonian and said, okay, now we don't need this. Let's simply simulate the decay model without really, doing anything. And in this sense, yeah, so these 2 pictures would be not equivalent in the case of many-body physics. It's only equivalent if you look at a single particle physics. So cavity QED, quantum Rabi model, could be simulated by spin orbit coupled BEC, but not the decay model, not the many-body version of a cavity QED, right? Yeah, so. So actually, what is really happening when you have this spin orbit coupled BEC? What is it equivalent to? Then it is equivalent to many copies of a quantum Rabi model, right? So this is as if, at least in the non-interacting case, this is as if you have many quantum Rabi models, and they are not talking with each other, and in this sense, it's single particle physics. It's not equivalent to the decay model. And yeah, so just to conclude this simple talk, so spin orbit coupling splits into a collective center of mass spin channel, and this is decay-like interaction, and many asymmetric relative mode channels, And yeah, so asymmetric relative mode couplings destructively interfere, cancelling the collective spin squeezing and many-body entanglement. And this mechanism explains why SOC-BECs, despite formal similarity to cavity QED, fail to show genuine collective effects in practice. And yeah, so actually, if you want to achieve squeezing in a SOC-BEC, you would have to have some method to selectively turn off one of the relative modes or the center of mass modes, and this would lead to some sort of squeezing. But I think it would be extremely hard to just pick one mode and then just turn it off in an experiment. And yeah, with this I would like to thank you, and also would like to thank my collaborator, Mohammed Hassan. And if you are interested in this simple paper, this recently appeared on arXiv. So thank you very much for the attention.
Thank you, Karol. Do you have some questions? Yes, please.
So thank you for this. You've done a service to everyone by solving this. I've always been a little suspicious of these results because in my language, these Hamiltonians altogether are bilinear in field operators. So I'd have said they transform coherent states into coherent states. So I was always a little perplexed by how this mechanism could work, but I never knew why it didn't work.
Yeah.
So thank you.
Yeah, you're welcome.
If not, maybe I can ask, because you show us that there is no possibility to generate spin squeezing as the two terms cancel each other. What's happened if you would add interactions?
Oh yeah, this is a good question. I don't know what happens. I mean, I imagine you would generate some squeezing because, you know, you would just have interactions between atoms, and this probably would lead to squeezing, at least if you consider two-body interactions. But if, I think there is one paper actually about this, but yeah, we didn't investigate it so far in detail.
Thanks. Actually related to the comment on squeezing versus bilinear or not, if you do include spin conservation, then it should enter as a square root, which is a highly nonlinear function. And then you could potentially get squeezing from there. Or at least below Dickey transition, and I'm talking Dickey now, right? Below Dickey transition, you should see squeezing until you reach the Z2 symmetry breaking. But then I don't know, so you're showing that at least when it decouples to a collective of Rabi models, then they cancel each other.
Yeah, so it's essentially this. Yeah, so this would be the full Hamiltonian, and then you have this mechanism that would really which would really create squeezing with the Z2 symmetry breaking, as you said. But you also have this mechanism, and if you just count them in, just everything cancels, and you have no net squeezing. This is the best explanation I have.
Okay, cool.
More questions?
Yeah, very nice, thank you. Usually in these cavity systems, you also have dissipation. Do you think that will play a role in how much squeezing you can experimentally generate?
In which case, actually?
The loss of photons that carry away, like...
Okay, so in the context of cavity QED, so this really depends what you really do in an experiment. So whether the coupling is inherent coupling from real light matter interaction, or whether this is simulated by some extra field, like with the laser. And I think if you have this, of course, if you have this simulated coupling through the laser, as in the experiment of Tillman-Esslinger, then definitely dissipation will remove or maybe prohibit squeezing, so you'll have definitely less. And in the case where you have the interaction between the light and matter, which is inherent from just light matter interaction, is not simulated, then you need to rethink what does it really mean that you squeeze something, and what is the observable of your system. So this is a little bit tricky, I would say.